and extending torsors. The main object I will be using here are schemes. You can think about a scheme as a generalization of an algebraic variety, which is the set of solutions of a set of polynomials. An algebraic a scheme is locally the spectrum of a ring, and you endow it with the topology, which is the Zariski topology, and a sheaf structure. And given a scheme S, I will call a group scheme over S, G a group scheme over
Excuse
S.
me, Sarah.
Yeah.
If you could just switch to a full screen, because it's
Yes. Yeah. The problem is that I cannot write over the papers when I put the full screen, but
okay, no problem. Okay.
I will see what to do. So I said that a group scheme over S is the data of a scheme over S together with the group law, the inverse, and the identity section. And but this is not this definition is not very suitable in practice, and I will give here. Well, we will rather think about group schemes in terms of their points. And I will say that the T point of G is an S-morphism of schemes T to G. And I will write for the T points of G morphisms from T to G. And I said before, we will think about group schemes in terms of their points. So a group scheme is a functor whose points are groups. So G of T is a group. To give examples, I have the additive group scheme. This is the functor, the group functor, which goes from the category of schemes over S to the category of groups, and associate to an S scheme T the global sections over T. We have the multiplicative group scheme GM over S, which is the functor which associates to an S scheme T the invertible global sections over T. We also have the group of nth root of unity, which is a subgroup of this one, and the T points of this group scheme are the T points from the multiplicative group, well, the invertible global sections whose order divides n. And finally, given an abstract group G, we can define the constant group scheme associated to G by taking copies of S with G inside G. So the multiplicative map here is given using the multiplicative map of G. So when I will be talking about Z over NZ, well, Z over NZ I will see this as a constant group scheme over the base. So it's, for example, if this is over some base S, this is just the copies of S with A inside Z of NZ. Now I have this sequence of group schemes, and I would like to give a meaning for this sequence to be an exact sequence of group schemes. And the first idea that comes to mind is to ask that this sequence is exact on points, which means that to any S scheme T, I have an exact sequence here of groups, since these are just groups. But when we see examples, we note that this is a too strong condition. For example, when K is a field, so when the base here is the spectrum of a field, take for S to be the affine scheme spec K. I take for G2 to be the multiplicative group over K, and G3 to be the multiplicative group over K. Here, the map is just taking an element here to the nth power. So the kernel of this map is mu n, the nth root of unity. Yeah. And now I compute these group schemes on the K point. So here it's mu n k of spec k, and on practice we don't write spec, we just write k here. Here gm k of spec k. So I recall that the K points of the GM, according to the definition of the multiplicative group, are invertible global sections. Global sections here are K, so taking the invertible global sections of K is just taking K star. So I have here K star to K star, and here it's the taken to the power n. And the fact is that this map is not surjective in general. So this is not an exact sequence in general. This is not surjective because if I take an element here, alpha in K, there is no reason to find beta in K such that beta to power n is equal to K. But we can always find a finite extension of K which contains a preimage of alpha. So if I take alpha in K star and I take K prime to be this field, this is a finite extension of K, and this contains a preimage. Well, no, sorry. I take here beta to be the nth root of alpha. So if I take this finite extension of K, then I have a preimage here of alpha. And this suggests to say that a morphism G2 to G3 of group schemes is surjective if so on points I will not look for a preimage of X on G2 of T, but I will allow to take a base change T prime over T, so to take another scheme T prime over T, such that I have a preimage inside G2 of T prime. And in fact, this idea leads to the definition of what we call Grothendieck topologies. Grothendieck formalized the topology, and in the classical topology, we take the open subset, the open subsets to be, well, inclusions, to come with inclusions mapped like this. And now, if X is a scheme, to define an open set on X, we will allow to take schemes that come outside from X. So we will only put a condition on the map that map this open to X. For example, for étale topology, we will ask the map here to be étale, which means flat and ramified. For fppf topology, we will ask this map to be fppf. For example, here, this sequence, as I said, in the classical topology, which is Zariski topology, this is not an exact sequence because it's not surjective here. But in the case where n is prime to the characteristic of K, this is an exact sequence on the étale topology. And the reason is that here I take a base change, which is spec K prime to spec K. Here K prime is an extension of K, a field extension of K. And in fact, this in the case where n is prime to the characteristic, this is a separable extension of K. And so this map is an étale map, which means that this is open in the étale topology, which means that this will be surjective in the étale topology if n is prime to the characteristic. Now, if n is not prime to the characteristic, this is not always an exact sequence, but in fppf topology, fppf means faithfully flat and of finite presentation. This is always an exact sequence. So according to what we want to study, we choose the topology that is more suitable to what we want to study. For example, here to study the p torsion on characteristic p, we need this to be an exact sequence, so we will need the fppf topology, and in my work I will use the fppf topology. So and now I can define what a torsor is. If E is a set and G a group which acts on E, we will say that E is a G-torsor if the action of G over E is free and transitive, which means that to any 2 points X and Y on E, there exists only one element of G which sends G to Y with the action. This is equivalent to say that this map given by the action of G over E is bijective. To give examples, if I see G acting on itself by translation, then G is a G-torsor. The action of G on itself is free and transitive. And this is what we call the trivial torsor. As another example, if I take 2 points on the affine plane, then there is only one vector which sends a point to the other. So the action of the vector space of the plane is free and transitive over the points of the plane. So the affine space is the torsor under the action of the vector space. And here what we note is that, for example, in this example, when I take the affine space and I fix a point there, on a point there, then I can build a bijection to the vector space. So whenever I fix a point, I have a bijection to the vector space. So this leads me to the trivial torsor. So I can see this as a trivial torsor since it's bijective to the group which is acting on it. And in fact, if the object here is a set, like here, I always have such trivialization of the torsor. So taking objects to be sets is not very interesting. This is why I will enlarge the category of objects I'm working with, and I will define the torsor in a larger setting. So I take X to be a scheme. I take G to be a group scheme over X. I will say that, well, Y is a scheme over X. This morphism is faithfully flat, and G acts on Y, and I will say that this is a torsor if the action of G over Y is free and transitive, which is equivalent to say that this morphism given by the action of G over A is an isomorphism. And in a similar way, in an equivalent way, we say that this is an equivalent definition. We say that Y over X is an fppf G-torsor if locally for the fppf topology, this is a trivial torsor, which means that locally we can find an fppf cover. This is an fppf map in the fppf topology, which means that this is the open for the fppf topology, such that Y, when I restrict Y to xy to xi, then this is the trivial torsor, which means that this is isomorphic to G times xy over xy. So this is the definition of a torsor. And in fact, if the group scheme here is étale, then the G-torsors are just the étale covers. And étale covers is the natural generalization of covers that we have in topology. But more generally, if G is just a group scheme, which is, for example, finite and flat, and not necessarily étale, we do not have an equivalent in topology. So now I can give more elaborated examples. If I consider L over K to be a finite separable extension of fields, then this morphism is a finite étale morphism because L over K is separable. And if in addition, I suppose that this extension is normal. So this is a Galois extension. And if I write G for the Galois group, which is automorphisms of L that are the identity over K, then we get this isomorphism, which is defined by the action of G over L. It is not hard to prove. Here, since L is a separable extension of K, I can write this with alpha an element of L. So taking this tensor product is taking this tensor product. K of alpha can be written as K of X over the minimal polynomial of alpha on K, which is denoted F here. So this is equal to this by extending scalars. Now F is a separable polynomial, so it has its roots are with multiplicity 1, so I can factor it like this. And this is the degree of the extension, which is the degree of F. So from here to here, we use the Chinese theorem. So I have the product of these rings. Now L of X over X minus alpha I is, every element here is isomorphic to L. So I have copies of L. The number of copies is the degree of the extension. And here, since the extension is Galois, the degree of extension is equal to the order of G, the order of the Galois group. So I have L copies of G of L with G and G. This is equal to, this is where I write G times L. And so I have this morphism of rings. So this gives me this, or morphism of fields. So this gives me in the scheme setting by taking the spectrum here, I get this morphism, which is an isomorphism, since this one is an isomorphism. And here, this is defined by the action of G on over spect L. And so the action is free and transitive, which means that spect L over spect K is a torsor under the action of G. As a second example here, you know, this, if C is a curve here, this is the pK group over C. So you have isomorphism classes of line bundles. And in fact, this group, this cohomological group, so this one is isomorphism classes of GM torsors over C. So in fact, a GM torsor, you can think about a GM torsor over a curve as a line bundle over a curve. Now, if I take K to be a field and I consider the curves given by y squared equal f of x with f here, a polynomial, non-constant polynomial, then the curve is a ramified cover of P1 of degree 2 under the group Z over N2Z. And here we do not have a torsor. And the reason is that, as I said in the definition, a torsor is locally isomorphic to the group, is locally isomorphic to the trivial torsor, so to the group which is acting on it. And here, this map is ramified, but the group which is acting here, which is Z over 2Z, which is a group scheme over spect K, the base here. So I said before that this is just a constant group scheme. So this is 2 copies of spect K, and with the A on Z over N2Z. And in fact, this morphism is unramified, because, well, when you have a morphism of schemes like this, you can over a base which is a point here, or spectrum of a field. Unramified morphisms like this is just to say that X is locally locally disjoint union of separable extensions of K. And here I have spec K, copies of spec K. So this is a trivially separable extension of K. So this map is unramified, while this one is ramified. So this cannot be a torsor, because as I said, a torsor is locally isomorphic to the trivial torsor. So here I cannot have a ramified map here and an unramified group which is acting here. Now, we've been interested in the question of extension of torsors. Given a torsor defined over a curve, I would like to extend the torsor over some family of curves. Here, I explain the setting here. I denote R discrete valuation ring. This is a ring where I have only one maximal ideal and one which is a prime ideal. Well, primes are maximals ideals, so here I have only one maximal and one prime ideal. And I write K for the fraction fields of R. I write F for some morphism, some family of, you can think about this family of curves over spec R. And with generic fiber given by this. Here, generic fiber, I mean that X is equal to this X times when restricted to the generic fiber, which is spec K. So we change the base here. I take G to be a finite flat group scheme over K, and I consider an fppf G torsor Y over X. And the question of extending torsors consists of, first, I need to find what I call a model of G, which is a finite and flat group scheme over S with generic fiber isomorphic to G. So here this, yes, here S is spec R. So the generic fiber is isomorphic to G, which means that G times spec K equals G, isomorphic to G. And once I have a model for the group scheme G, I need to extend the torsor itself. So I need to extend the action of G on Y into an action of G, this G over the extended torsor, like this. And we know today that we do not have a general solution to this problem, but the question has been investigated in some particular cases. For example, the case where the group acting is a finite constant group with order prime to the characteristic of R is known to have a solution. Also, the case where X is a curve with good reduction, which means that it has a smooth model over R, it also has a solution. A more general case where this is supposed to be regular. Here we can construct an extension of the torsor, not over X, but over some scheme X prime, such that X prime is obtained from X with a finite number of blows up. And now, if we want to find a more general solution to this question, we see that the condition is too strong, because here I am looking for a model which is finite and flat, but if my group scheme admits a model which is étale, so it is finite and flat and unramified, so it is an étale, then, as I explained before, the torsor should be étale as well, because it's locally isomorphic to the group which is acting. But asking for this map to be étale or unramified is a too strong condition. So what we are going to do here is we are going to enlarge the category of torsors. And how we will do this, we will allow the torsors or the morphisms here to be ramified, even though if the group acting is unramified. And this will lead to the definition of log torsors. And to do this, we will need to enlarge the category of objects we are working with. So instead of working with schemes, we are going to add a structure on the schemes, and this will give what we call a log scheme. So I call a log scheme X a scheme provided with a log structure. This is OX here is the sheaf which comes with the scheme X, and I call a log structure the data of a sheaf of monoids denoted MX that maps to OX. So this is a pre-log structure, and I will say that this is log structure if the inverse image of the invertible elements here is isomorphic to the invertible elements here. This is a log scheme, and we note here that this is inside MX, so in particular, MX contains all the invertible elements here. So the first example that we take for the MX is to take MX equal to the OX star, so the invertible elements here. And this is what is called the trivial log structure. So if I consider the category of schemes to the category of log schemes, I have a map from here to here. To a scheme X, I associate a scheme endowed with its trivial log structure, and in fact, this is a full embedding, which means that considering the trivial log structure on X does not add any new morphism. So more interesting log structure on X is if X is regular, and if I consider an open Zariski open U on X whose complementary is a divisor, then this allows me to define a log structure on X, which is the direct image of the trivial log structure on U. So the functions on this sheaf are just the functions that are invertible on U. So these are functions which admit zeros and poles outside U. And this log structure, by definition, is trivial over U. And in fact, this is a log structure that I will be using here. Here, my X will be the spectrum of a discrete valuation ring, and U will be the spectrum of its fraction field. This is open inside spect R. And the divisor will be the spectrum of the residue field. And so my log structures, I will call this the canonical log structure on a discrete valuation ring. So my log structure is always trivial when I restrict to the generic fiber. Now, if I consider X a log scheme, which comes with a log structure denoted MX, I denote P a monoid, and if I have a morphism of sheaves of from P to the sheaf MX, so this gives me, by definition, a pre-log structure since this goes to OX. And in fact, there is a canonical way to associate to any pre-log structure a log structure on X, and we say that P is a chart for this log structure if the associated log structure is isomorphic to MX. So it's the log structure which is already in MX. For example, if A is a discrete valuation ring, I said before that we have a canonical log structure on spect A, which is given by the divisor. And in fact, we can find a chart for this log structure, and this chart is modeled on the sheaf. The sheaf is the constant sheaf equal to n, which is the ring of integers. Here, if I call A is a discrete valuation ring, so it has a unique maximal ideal, rated M, and this is a principal ring. So this is generated by an element, say P, and this is what I call the uniformizer. And this chart is given by to one I associate. So to one I associate this this uniformizer. Now, I will consider here in my work log schemes which are fine and saturated, which means that these are log schemes which are modeled on charts, so on monoids P that are fine and saturated. I'm not going in details here, but this is important for me as we will see later. And I can endow the category of log schemes with a topology which is called Kummer-log flat topology, and which is what is important here to know is that, well, when I have a Kummer-log flat morphism of log schemes, then when I go back to the generic fiber or where the log structure is trivial, then I get an fppf map. So this is like a generalization of the fppf topology on the category of log schemes. Now, I will give an example of a log torsor, which is not an fppf torsor, to see that adding this log structure really adds new torsors. So I take A to be a discrete valuation ring with a uniformizer denoted B. I write B for this ring. In fact, this is also a discrete valuation ring with uniformizer given by the nth root of B. I write G to be the automorphism of B, which fixes A. So an automorphism of B just given by choosing an image of the root of unity. So this is equal to mu n. And here, given the hypothesis I have here, the fact that n is invertible in A and that A contains an n primitive root of unity, this will imply that mu n is isomorphic to the constant group Z over NZ. Here I take so X to be the affine scheme spec A and Y the affine scheme spec B. So G acts on B, and I write here this map, this morphism for the action of G over Y. And here the fiber product of Y and Y as log schemes is computed in the category of fine and saturated log schemes. So as I said before, so Y is a log scheme with the canonical log structure given by, because it's a discrete valuation ring. And I said before, I have charts for this log structure. So the chart for X is given by N to A. This is the global sections of X. So one, I send the uniformizer of A, sorry, and the same for Y. And the morphism of log schemes from Y to X is given in the level of, so the morphism of log schemes, so I have a morphism of schemes, the underlying schemes, and I also have a morphism of the log structure. And to give a morphism of log structure here, it's enough to give a morphism between the charts. And here, the idea is I need to send this uniformizer to the uniformizer of A. So the law here is written additively. So I send A to A times N. And now I want to compute this fiber product in the category of log schemes. In the level of log structures, I need to compute the push out of these monoids. And the fact is that, well, push out, or what we write also the amalgamated sum. Here, this push out, which I write like this. The fact is that this is not always a fine and saturated monoid, but I want to compute this fiber product in the category of fine and saturated monoid. So I need to get a chart which is fine and saturated, but this is not fine and saturated in general. But there is a canonical way to associate to this fine and saturated monoid, and if we compute the associated fine and saturated monoid to this, we will get copies of n over z over nz. So what we remark here is that this one is the same as the chart that we have here. So I recall that this is just copies of y with g in g. So a chart for this is just given by copies of n is a chart for y, with g inside z over nz. So this log scheme and this log scheme have the same chart, which means that they have the same log structure. And in fact, this is an isomorphism of log schemes, of fine unsaturated log schemes, which means that since this is the action map of the action map of g over y, which means that the action of g over y is free and transitive. And this is what gives me what we call a log torsor. And what is important here is that I computed this in the category of fine unsaturated log schemes, because if I didn't computed this in the category of fine unsaturated log schemes, I would not find this for the chart. So the chart for this and this will be different. So I will not get the same log structure here. So this will not be an isomorphism of log schemes. But taking the fiber product in the category of fine unsaturated log schemes gives me an isomorphism here. So this is so the action of g over over y is free and transitive. But this is not a torsor in the classical definition. This is not an fppf torsor, and the reason is that here g is z over nz. So this is an unramified group scheme, as I said in the beginning, and y over x, which is so spec b to spec a, which is the same as giving a map from a to b, which is taking the nth root of b. This is a totally ramified map, so this is not unramified. So this cannot be a torsor, an fppf torsor, but this is a log torsor. And the idea is that the idea here, so I have a morphism of log schemes here, which is ramified, and the group actin is unramified, but I still have a torsor. So considering log torsor is tolerating to have ramification for the torsor. So I write here the definition. I will say that, well, if X is a fine unsaturated log scheme and G a group scheme over X, I will say that Y over X is a torsor if this map is a Kummer-Log flag map, and if G acts on Y, and if the action is free and transitive. And so this, which means that this is an isomorphism of fine unsaturated log schemes. And since the idea here is to allow having a ramification, for example, if you want to compute the GM torsors, log torsors, I recall that I said that GM fppf torsors are just fppf torsors are to give a GM fppf torsor is equivalent to give a line bundle. So a divisor, some Cartier divisor, so a divisor with integer coefficients. And in fact, here, since we allow the ramification, when I consider the divisor associated to a function, I will allow to consider the divisor associated to nth root of a function, even if it ramifies on the zeros of f. And I will put that this is 1 over n, the divisor associated to the function. And the result is that the GM torsors here, the GM log torsors, are just divisors that appear with rational coefficients. So yes. Yes, this is what I plan to say on the first part. So